Okay, in this example, we're going to look at that video of the guy jumping off the roof. So here he is up at the top, just leaving the roof. And if you can see right here, he is about to hit the trampoline at this point. So if we look at the energies between these two, up here we're going to say that all of this guy's energy is stored gravitational energy. Right before he hits the trampoline, which we're choosing to be our reference level, all of his energy is going to be movement. So when we make our quantitative conservation energy equation, we're going to see that Eg equals Em. Let's see if we can solve something from this. If we expand this out, we get mgh equals 1/2 mv squared. We're going to say the mass of the jumper is 60 kilograms and the height above the trampoline is 5.5 meters per second. So just like the last one, let's see how fast he was going right before he hit the trampoline. I said it in the last time, you can actually get rid of the mass. It does not matter what the mass is. So if we rewrite this equation, m is on both sides, we can cancel that out actually. And so actually we only need the height and we can figure out how fast it should be going. So gravity, 10 meters per second squared times 5.5 meters equals 1/2 times v squared. All right, 5.5 times 10 is 55. Is 1/2 v squared. 2 times 55 is 110 equals v squared. And so we have the square root of 110. 110 square root gives us 10.4, let's say 9. So the velocity equals, we'll just say 10.5. 10.5 meters per second. All right, we're going to jump right into this next one and say, let's look at that stored gravitational at the start, but now let's look at a different point where he's actually in the trampoline and the trampoline has been stretched this distance from here to here. Okay? So let's look at, we can analyze this. We have some stored gravitational. We don't have any stored gravitational when he's stretched out to the bottom. He's no longer moving at the bottom. But we have some elastic and some thermal that's gone into the springs. So let's say, in this case, 1,500 joules of energy has gone into thermal. That's what we're just going to say. We've lost 1,500 joules to thermal. Can we figure out the spring constant of the trampoline? That's our question. So let's start with our quantitative conservation energy equation. Eg at the start must equal EE plus E thermal. So notice we've got a totally different equation. No longer looks like the ones we've done before. So it's just saying the energy at the start and the energy at the end. Eg is mgh. EE is 1/2 the spring constant times however far the stretch is plus E thermal. So let's bring it down here and let's put in some values. The mass of the jumper, 60 kilograms, times 10 meters per second squared, times the height of 5.5 meters. These are just values that we calculated from right here. Must equal 1/2. Well, we're looking for the spring constant. Oh, sorry, I was off there. We're looking for the spring constant of K. So we're going to keep that a variable. And we're going to, sorry, this won't be x squared. We're going to put that value in. It's 0.5 meters. 0.5 meters squared plus the thermal energy of 1,500 joules. All right, let's calculate this all out. So we've got 60 times 10 times 5.5 gives us 3300, that's in joules, is equal to 1/2 K Let's simplify 0.5 squared. 0.5 squared is going to give us 0.25 plus 1500 joules. We can subtract these 1500 joules. Joules there. So this is going to give us this 1800 joules is how much energy is stored in the elastic. This 1800 joules is how much is stored in the elastic, because we've taken the gravitational up here and we subtracted the thermal. So all that we have left is our elastic. So that's going to equal 1/2 the spring constant times 0.25. So to solve for K, we multiply this 1800 by 2. 3600 equals K times 0.25, and we divide both sides by 0.25, and we get that K equals 14,400, and the unit on that is newtons per meter. So hopefully this video has shown you a couple ways that you can use the quantitative conservation energy equations to look at what energies you have at the start and look at what energies you have at the end, and build a quantified equation with known equations for each of the energies and solve for unknowns. That's what we're going to be doing on worksheet 3 and a little bit into next week.